This section, we're talking about fluids. And fluids are an interesting topic. So, first question, what in the world is a fluid? So, here's the various states of matter: solid, liquid, and gas. And the volume of a solid is constant, its density is constant, its shape is basically constant unless you reshape a solid by pounding on it. A liquid, its volume is constant, its density is constant, its shape, though, is variable. You pour a container of liquid into a different shaped container, it immediately takes that shape. And of course, a gas, its volume is variable depending on the pressure, its density is variable, and its shape is variable. You easily fill any shape you have. Now, I noticed a little asterisk I put here on constant volume and constant density. Technically, liquids are slightly compressible. We'll talk in this case particularly. So, for example, at the bottom of the Marianas Trench, which is the deepest part of the ocean, water is compressed about 5% due to this incredible pressure of about 1,000 atmospheres or 1,000 bar. Because of that, its density slightly increases. We're going to take those extremes out of this chapter and just assume that liquids are incompressible and its density, therefore, is constant. But what do we mean by a fluid? Well, a fluid is anything that has a variable shape that can flow and take the shape of its container. So both liquids and gases are considered fluids in this unit. Most of the time, we're going to spend our time with liquids in this unit, but please realize that gases are also considered to be fluids. So, what are we going to study in particular? In this first section, we're going to look at fluid statics. Statics meaning stationary fluids. We're going to look at the density, the pressure, and the buoyant force using something called Archimedes' principle. Buoyant force is what, for example, keeps this little rubber ducky floating against the force of gravity acting downward. So, first of all, density. Most of you know this either from middle school or from chemistry. The formula for density is mass over volume. Where this looks like a funny letter P, it's the Greek letter rho. And rho is used in physics for any quantity per unit volume. In this case, we're going to use it for matter density or mass density, which is just mass over volume. The other thing I need to mention is this. In chemistry, you typically measure density in grams per cubic centimeter or grams per milliliter, same thing. But in physics, since our base unit for mass is the kilogram and our unit for length is the meter, we'll be measuring it in kilograms over meters squared. And so if we do that, some of the familiar densities are a little different. For example, in chemistry, you know that the density of water is 1 gram per cubic centimeter. Well, in physics then, take a look at the difference. It becomes 1,000 kilograms per cubic meter. The other ones on here are fairly small. Air at STP is about 1.2 kilograms per cubic meter. Seawater is a little bit more dense than fresh water. Honey, more dense than seawater. And then we get to metals. Aluminum, fairly low density. Iron, pretty high density. Lead, extraordinarily high density. But osmium is actually even more dense than lead. In fact, almost twice as dense as lead. You might say, why don't we use osmium? It's way too expensive and rare, way too rare. So lead's easy. Osmium, not so common. So take a quick look at this, real quick plug and chug. So for a given material, various masses of it, we measure its volume from probably like a junkyard. The question is then this. If we want to graph this data, how do we graph it so that the slope is the density? Now again, remember in the equation, rho represents density. And if you look at this, then perhaps it's intuitively obvious, oh, wait a second. It should be just mass over volume. If we do that, we graph this data, it should be linear, and the slope, which is rise over run, is going to be mass over volume, which by intuition, is going to be equal to rho, the density of the material. So the question is, what is the density of this sample? Well, to save a little bit of time, I went ahead and graphed it in Excel. So here it is, a mass versus volume. Actually realize I have the title wrong on this one. Mass versus volume graph. And notice the graph is beautifully linear. But take a look at this real quick. You remember, of course, that I am unhappy with the incorrect variables here. And, of course, the slope in y-intercept should have units. In this particular case, I'm going to drop the y-intercept. Why? It is so small in comparison to my slope. Yeah, I'm just going to say this is 0. But what's the equation? Well, the y variable is mass. The x variable is volume. And my units for my slope, if you think about what I'm graphing to get this slope, the rise here has units of kilograms. The run here has units of meters cubed. So my slope has to have units of kilograms over meters cubed. What's my formula going to be? It's going to be this. Mass, that's my y variable, equals the slope, 7,870 to 3 sig figs, kilograms per cubic meter, that's from the slope here, times my x variable, which is going to be volume. What's this material? Well, if you look at the previous table real quick, this is most likely iron right here. All right, this one's a really quick practice one. This time we have 5 different objects labeled A, B, C, D, and E. We have identical masses, or not quite identical masses, but a bunch of masses of it, and its volumes measured in cubic meters. I would like you to rank these from greatest to least density. I recommend pausing it for just a brief moment so you can try it. But here we go in 3, 2, 1. Here's the densities, just taking the mass divided by the volume in each case. And then you can rank them very quickly. The most dense material is D. It's probably osmium. Down, the second one looks like iron. Third one, I have no idea what that is. I gotta look at the table again. Down to 2, it looks, down to 4, and then down to 5, which looks like fresh water. And so you can kind of see them. All right, here's a quick practice problem. The cubical box shown in the figure has edges of length 0.5 meters. The box, which has negligible mass, is filled with 125 identical spheres that each have a density of 100 kilograms per cubic meter, sort of dense styrofoam, and a radius of 5 centimeters. What's the average density of the box with the spheres inside? Well, how do we figure out density? Well, we've got to figure out the total mass of the box divided by its total volume. Well, the total volume's easy. We've got length, width, and height right here. But we got to figure out the mass of all the balls that are inside of it. To do that, we're going to have to actually figure out the mass of each ball. Well, the volume of one sphere would be 4/3 pi r cubed, if you remember your equations for volume. So plugging in our 5 centimeters for the radius, we get that the volume of one sphere is that. Well, how do we figure out the mass? Well, if you take the density equation and solve it for mass, multiplying both sides by v, you'll get this. The mass of one sphere is going to be the density of a sphere times its volume. Well, we just figured out the volume up here, so we can plug that in there. The density is 100 from up here. And we'll figure out the mass of one sphere is that many kilograms. So what's the mass of 125 of these spheres? Well, we just have to take, we'll go ahead and plug it in here. The mass of all those is just going to be 125 times the mass of one sphere, which we just found right here, divided by the volume, which is 0.5 cubed. 0.5 times 0.5 times 0.5. And if you solve that, you get the overall density of our box is incredibly low, 52.4 kilograms per cubic meter. For those of you who are real astute, please realize, yes, I realize the in between the spheres is filled with air, which has a density of 1.2 kilograms per cubic meter. So you could mess with this a little bit, but the trick is trying to figure out that volume. All right, pressure is our next topic. Why am I showing this x-ray of a woman wearing a stiletto heel and this elephant? Well, believe it or not, the pressure at the bottom of a stiletto heel is the same as the pressure on the bottom of an elephant's foot. You might say, wait, how is that even possible? Well, if you remember, pressure is defined as force over area. In this case, the elephant, of course, weighs much more than the woman, but that force of the elephant is spread over a much larger area. Where in this case, the weight of the woman is spread over just the stiletto heel. Stiletto heels will put dents in most floors, so will so will elephants if you have them step on most floors. Believe it or not, pressure about the same. So pressure is defined as force per area, where force is measured in units of newtons, area measured in units of meters squared. If we use that, we end up with the unit of pascals, abbreviated capital P small a. Pascal is a relatively small unit, so in chemistry you tend to use kilopascals. Atmospheric pressure, just the weight of the air on top of us, is about 101,300 pascals, or 101.3 kilopascals, which we oftentimes just refer to as 1 atmosphere or 1 bar. In chemistry, you may have used millibars as well, thousands of bars. And just a real quick practice one here. Is the pressure in each of the tires of my SUV. And by driving the tire over a piece of paper, I traced around the bottom of each of the tires. So this distance, or this little piece I'm circling over here, is the contact area. I just measured length times width and got basically the contact area between the ground and each one of my tires. My question is what's the weight of my vehicle? And you're like, whoa, wait, how can you solve that? Well, we can actually figure out the force by rearranging this question or equation. Force is going to be equal to the pressure times the area. Now, please forgive me, I used imperial units in this case, just because I knew the pressure in my tires in pounds per square inch, and I could calculate the contact area, and I did that in square inches. The pressure here is pounds per square inch, which is oftentimes referred to as PSI. That's literally what it stands for, pounds per square inch. So what's the force in this case? Well, just taking that pressure times the area gives me that for the first one, and here are the other ones. So if that's the force being exerted by the tires and the ground, that's also the force that the ground is exerting upward on the tires. So what's the total weight of my car? Well, it's the sum of those four forces. Or in this case, it comes up with roughly this many pounds. Now, one interesting thing. Here's my car. It's a 2011 GMC Arcadia. Its gross weight, according from the manufacturer, even with a full tank, depending on the accessories, is somewhere between those two values. I'm way above that. So my question is, assuming I measured the areas correctly, why is my value too big? And the answer is, I'll let you think about it for a brief moment, is my area is actually a little bit too big. Why? Because of the tread on my tire. The tread, these little gaps here, are actually not in contact with the floor. When I calculated the area, I did not subtract these missing points of contact. And so my area, all in this case, was a little bit too big, which means my force was a little bit too big. Not a lot. You can see my numbers here are only over by about 10%, but, well, less than 10%. But it still was enough to create a small defect in my answers. Take a look at this AP multiple choice question. The student argues that the pressure exerted on the table by identical bricks shown is greatest in case X. Is the student's claim correct? Well, in this case, the force of gravity is the same for all three of these. So the force that the table is exerting upward on all these is exactly the same. But which one has the greatest pressure acting on it? Well, the one that has the smallest area of contact, which I would argue is probably Z. That force is just over this small area of this rectangular solid. Whoops. So which is the correct answer on this one? The answer, of course, is no, he's not correct, or she's not correct. But is it C or D? No, because the pressure is the same regardless of orientation. That is not true because the area is changing. Correct answer on this one is D. No, because the pressure decreases with increasing surface area in contact with the table. Yeah, X has the smallest pressure because it has the largest area in contact with the table. Take a look at this one, a little bit more challenging. Two cubes made of the same material and with the same density rho. The pressure that A exerts on the table is PA, and the pressure that cube B exerts on the floor is PB. Which of the following answers correctly relate these two quantities? Pause now if you'd like to actually work on it yourself before I give the answer. In 3, 2, 1. First question, are the masses of these two the same? If we assume the mass of this one is m, what's going to be the mass of this one? Well, if you quickly work it out, because of the sizes, this one's going to have a volume of s cubed. This one is going to have a volume of 2s times 2s times 2s, 2s cubed, or 8s cubed. Assuming it's the exact same density, and if you rearrange this, whoops, I don't have the density equation here, density is equal to mass over volume, you can very quickly see that the mass is going to be equal to rho times the volume. If this one has a mass of m, this one's going to be 8 times the volume and 8 times the mass. So you're like, okay, good. So the pressure on this one is going to be 8 times bigger on cube B. But there's one other thing to consider. And it's not drawn here, so I'm going to kind of just draw in the background. Whoops, I'm not doing a very good job. Pretend that I actually complete this cube. They didn't give us any three-dimensional view of it. But what portion of it is in contact with the floor? Well, it's this piece right here. What's the area of that piece? Well, that area is s squared. What about this one? Well, this one's going to have a much larger area in contact with the floor. It's going to be 2s by 2s. The area of this is going to be 4s squared. So we have 4 times the area. Since pressure is force over area, how's the pressure on cube B compared to cube A? Well, the force of gravity on the second one is going to be 8 times larger. But the area goes up by a factor of 4. So how does the pressure on cube B compare to cube A? This one should have twice the pressure on the floor as this one. So which one of the answers is correct? Correct answer on this one, most accurate one, is C. Yes, the pressure on that is, not greater than that. Oh, sorry, I misread that. Yeah, it's this one. We move into our last topic in terms of fluids. We've talked about pressure already. What's the pressure on a fish due to the weight of the column of water that is directly above the fish? So I'm going to draw a little column here and give it a few dimensions. Let's say that this bottom is S by S, sort of using the same kind of notation, and the height of the column is H. You could also think about that as a depth. Well, to answer that question, first of all, I have to figure out the mass of it. Again, we're going to use that same trick we did before. It's going to be equal to density times volume, just rearranging the density equation. In this case, the volume is going to be s squared times h. The area of the bottom of my rectangular solid times its height, which is going to be h. How do we figure out the weight of that water? Well, the weight of the water is going to be equal to the mass of the water in that column times gravity. Well, we know the mass is going to be equal to that, so I can substitute in this entire, this entire quantity for the mass. Let me take out that middle part there, sorry, in the wrong space, which is just the complete answer from up here for mass. How do we get pressure now? Well, pressure is just force over area. In this case, the force is the force of gravity on that column of water. And the area is just going to be s squared, the shaded area I put over here. You'll notice something interesting. The s squareds cancel. So what is the pressure at that depth? It's simply equal to rho gh, where rho is the density of my liquid, g is gravity, and h is the height of the liquid above that particular object. In this case, you can also think about that as depth. This is oftentimes referred to as gauge pressure. We'll talk more about that in a moment, but what we're talking about here is this. If you took a depth gauge would read 0 at the surface, and by the time you got down here, it would not be reading 0, it would read some other value. We consider that the gauge pressure, that increase in pressure just due to the weight of the water. We'll talk more about that in just a moment. Take a look at this. This is a nice PhET simulation. In this case, I remove the atmosphere. Don't actually try this at home. So I turn the atmosphere off. Water I know would actually boil, but in this case I've got a tank of water. And notice that the pressure at a depth of about 1 meter is about 10 kilopascals, just due to the weight of the water. And that should actually make sense. We just talked about gauge pressure is being equal to rho gh. In this case, density of fresh water is 1,000, gravity is 10, our depth is 1 meter. And so, yeah, we should experience a gauge pressure of about 10,000 pascals or 10 kilopascals, exactly what we read. Well, what if we put an atmosphere on? So now I've turned the atmosphere back on again. And so at the surface of the water, we get about 103 kilopascals. I know it should be about 101. Apparently it's a high pressure day. It's a very sunny day. I don't know why PhET used that number. But now look at what the depth is again at 1 meter of fresh water. Suddenly now it's 113 kilopascals. It was 10 before. What in the world is going on? Well, our gauge pressure is still 10. That's due to the addition of pressure just going from here down to here. But what's going on? What we're now measuring down here, this is actually what's measuring what's called absolute pressure. Absolute, I like to think about it as like total pressure. It's the pressure due to the atmosphere plus the gauge pressure. So in this case, our atmospheric pressure, as we're measuring right here at this point, just from the surface of water, is about 103 kilopascals. Our gauge pressure, from a calculation we did before, is 10, giving us an absolute pressure at that point of 113 pascals. This is a very useful one because oftentimes we have to deal with multiple things. So it's not multiple gases or fluids. In this case, it's the pressure of the atmosphere plus the pressure due to the water. In general, AP will write it this way. The absolute pressure is equal to the atmospheric pressure plus the gauge pressure, which is rho gh. If you take a look at this, here's a nice diagram of the Earth's atmosphere. And here we are, here's the pressure at the surface, about 101 kilopascals. And we'll call this the edge of the atmosphere up here at about 0. The question is, and there's a couple of interesting points on this, is what in the world is the pressure at a couple of these points? Well, At 6 kilometers, the pressure drops down to about at half the atmospheric pressure at the surface. What does that mean? It means you're above half the atmosphere already if you're at 6 kilometers above the surface. Where is that at for a different point? Well, the edge of space is oftentimes called something a little bit different, but for most people, we call it at about 100 kilometers. We call that the edge of space, where the pressure is zero. And you might say, wait a second, something's wrong here. At 6 kilometers, you're already halfway above the atmosphere, but you're not above all of it to get to 100 kilometers? Yeah, as you might have guessed, this is not a linear function. Why? Because the density of air changes, and you can sort of see it here. Very low density towards the top, very high density close to where we live here at the surface. And so, yeah, very interesting about compressible gases or compressible fluids. So in general, with that equation before, we've got the absolute pressure measured in pascals is equal to atmospheric pressure in pascals. AP uses just 10 to the fifth or 100,000 pascals or 100 kilopascals. Fluid density in kilograms per cubic meters. Gravitational field strength in newtons per kilogram. AP uses 10. H is fluid depth in meters. And rho GH, that entire term, is called the gauge pressure. So take a look at this one. In this case, we've got an open pipe. That is, it's open to the atmosphere. It's filled with water all the way up here to the top. And the question is, what's the pressure going to be here at the bottom of the valve, assuming the valve is still closed? The height of the pipe is 0.35 meters. We're given that the atmospheric pressure is 100 kilopascals. So the question is, what's the gauge and absolute pressure at the base of the valve? So solving this, first of all, the gauge pressure we know is just equal to rho GH. In this case, just the density of water times gravity times the height in meters. And that gives us about 3,500 pascals. So what's the absolute pressure? Well, absolute pressure is just equal to atmospheric pressure plus the gauge pressure. That's this equation up here. We already know the gauge pressure is 3,500. Atmospheric pressure was given to us up here. And so what's the absolute pressure? 103,500 pascals. You're like, wait, this is not too bad. Yeah, it's not bad at all. Let's take another example here. How deep underwater in fresh water, 1,000 kilograms per cubic meter, must a scuba diver go to experience an absolute pressure equal to 4 times atmospheric pressure? And I wrote it in shortcut notation, 100,000 pascals. Well, using the same equation, we want to know when this pressure is going to be equal to 4 times normal atmospheric pressure. That would be 4 times the pressure was given. Well, atmospheric pressure is still 10 to the fifth, and now the gauge pressure is going to have to equal this. And some of you can really see already that this is going to have to equal to 3 times the normal atmospheric pressure, plus this 1 is going to equal 4 times. Solving it, subtracting the 10 to the fifth from both sides gives us this, equals this side. And if you quickly work it out, it's about 30 meters down. Just real quick note, 10 meters of fresh water is about 1 atmosphere of pressure, or one that. So why is it only 30 meters then? Well, you already experienced 1 atmosphere at the surface, and this additional 30 meters gives you 3 additional atmospheres for a total of the 4 atmospheres we're asking for. All right. Last thing on this section is buoyant force, and it's a big one. We know that a submerged or partially submerged object has more pressure acting on the bottom of it than it does at the top. Why? We know that pressure is equal to rho GH, where H is the depth. So the greater the depth, the greater the pressure. And since force is equal to pressure times area, we tend to end up with more force along this bottom part than we do along the same area on the top because of the greater pressure down here. And yes, there's force on the sides as well, but that tends to cancel out. So we end up with a net upward force on the object. And this is a new force. This is not one of the four that we know already. So we're adding finally a fifth force. We had force of gravity, normal force, tension, and friction. We're finally adding a fifth force, a buoyant force. Again, reminder, centripetal force is not a new force. It's just the name we give the net inward force for circular motion. Archimedes' principle states the following. That upward buoyant force is just equal to the weight of the liquid displaced. In other words, the force of the gravity of the liquid that would have occupied this volume is how you figure out the buoyant force. And that's kind of an interesting idea. Here's a sketch of we think Archimedes looks like. We're not so sure. We can actually figure out an equation for that. Again, using our density equation, we can figure out the mass of the water displaced by this bowling ball would equal the density of the water times the volume of the water displaced. Or in general, force buoyant has to equal the weight of the liquid displaced. Well, we know the mass, that's this part right here. And so you can rewrite this just like this. Mass of the water displaced is equal to density of water times its volume times g, or in general, it's just written this way, rho gv. You're like, wait, isn't that the same equation? No, we had rho gh up on top here for pressure. One quick note though, this is the density of the material displaced, in this case water. It's not the density of the bowling ball. And this is, though, the volume of the liquid displaced, which is either the volume of the liquid displaced or the volume of the bowling ball. Take a quick look at this one. Quick sort of conceptual question. Object A and object B are submerged in the same liquid. Which one has a greater buoyant force acting on it? Correct answer on this one is B. Why? Buoyant force is just equal to rho GV. B is displacing more liquid, so it has a greater buoyant force on it. If the objects are moved lower in the fluid, will the buoyant force increase or decrease? Well, as you go deeper in liquid, the pressure is going to increase, but it's going to increase both on the top and the bottom. In this case, the difference in pressure is what causes the buoyant force. Notice the buoyant force doesn't matter on how deep you are, just the volume of the liquid displaced. So believe it or not, it's going to be the same. It's actually not going to change as you go deeper. Finally, one last question. If object A is made from styrofoam and object B is made from lead, which object will have a greater buoyant force on it? And you're like, oh, styrofoam floats. It's got to have a greater buoyant force. In this case, this was a quick check. Again, the buoyant force only depends on the volume and the density of the liquid displaced. Assuming this is just good old-fashioned water, both of these are going to be displacing water. The density for both of these is going to be 1,000, or the liquid displaced. And so B is still going to have a greater buoyant force than A. Doesn't matter what they're made of, just the volume of the liquid displaced. Now let's take a look at a more interesting one. The same 1 cubic centimeter cube displaced in water, which has a density of 1,000, and honey, which has a density of 1420. Question. First question before we get started. What's the volume of the cube in cubic meters? Naively, you might say, oh, okay, converting centimeters to meters, it's easy. We just move the decimal place over by a factor of 100, 2 decimal places. That's naive because you have to remember that volume is length times width times height. If we convert the 1 centimeter into meters, each of its dimensions is going to be 0.1 meters, length, width, height. And so what's that volume? It's 1/millionth of a cubic meter. So we had to move the decimal place over 6 places when we're converting volumes. My question now is, what's the buoyant force acting on each cube? You're like, oh, it's the same because they have the same volume. Yeah. In this case, it's equal to the volume of the liquid displaced. So the one in water is going to be the density of the water times G times the volume, and it gives us that many newtons. What's the buoyant force of the one in honey? Well, in this case, it's displacing honey, which has that density, and its buoyant force is going to be that. Which one has a greater buoyant force acting on it? In this case, the honey one. Will these cubes float? Well, we know the upward force on it, but do we know the mass of either one of these? The answer is no. Can we figure out which one's going to float? Probably not yet, unless till we know the force of gravity. So now let's take a look at this situation. Two cubes of the same volume are completely submerged in water. One's made of styrofoam and the other is made of lead. First question, what's the volume of each cube in cubic meters? That's the same as it was last time. So it's just going to be 10 to the minus 6 cubic meters. But now we can ask this question. What's the buoyant force acting on each cube? Now before we solve this, just think about this for a moment. They have the exact same volume. They're submerged in the exact same fluid. Which one's going to have a greater buoyant force acting on it? The answer is they should be the same. So solving it, we get this for the styrofoam and this for the lead. Again, notice that the density of the material that it's in is water, so we're using 1,000 for both. What's the weight of each cube? Well, now here's where things get a little bit different. Here, we're actually going to plug in the density of styrofoam here to figure out the weight of the styrofoam, or the force of gravity on it. That's going to be 33 times gravity times its volume, which is going to be 0.0033 newtons. And then for the lead, plugging in its density over here, and gravity and its volume, we get this. Now, you can actually see very clearly which one of these is going to float. Well, you can work it out. Look at the two forces on the lead, buoyant force and the force of gravity. Yeah, obviously there's a net upward force here of about 0.0967 newtons. And what about the lead? Well, the lead has got a net force downward of 0.1034 newtons. It's going to sink. You can even calculate the acceleration because you can calculate the mass of each one of these. You can figure out net force, and yeah, easily done. All right, let's take a look at another example. A solid mass of unknown material is completely submerged in water. What's the density of the mass? So outside of the water, you can see that the tension in the rope is 5 newtons, which means the force of gravity on this is also going to be 0.5 newtons. That immediately allows us to calculate what the mass needs to be, or what the mass must be. Using gravity equals 10 meters per second squared, or 10 newtons per kilogram, the mass in this case has to be 0.5 kilograms. Sorry, the force of gravity here is 5 newtons. My apologies. I got ahead of myself when I started writing the other one. And that's also going to be the force of gravity over here. Force of gravity does not change when something's submerged. The question I want to ask is, what's the buoyant force acting on this mass? Well, to solve that, we can look at the tension and the force of gravity. There has to be an additional upward force on this thing. How much? Well, you can kind of work it out. Just the difference between these two. The buoyant force here has to be 0.57 newtons. So the sum of the buoyant force plus the tension gives us the force of gravity. What's the volume of the mass in cubic meters? You might say, wait a second, how can I solve that? Well, believe it or not, just from the buoyant force. Remember, the buoyant force is equal to the density times the gravity times the volume of the liquid displaced. In this case, we know the buoyant force, we know the density of the water, we know gravity, The only thing we don't know is what the volume of the water is being displaced, which will be equal to, in this case, the volume of our mass. In this case, it's that. And now we can actually solve for the density. Density is mass over volume. We already know the mass is 0.5 kilograms. The volume we just solved over here, using that down here, you can calculate the density of this mass is about that. Most likely it's brass, based on that number. Take a look at this one. What fraction of an ice cube height is above the water? In other words, if this is the ice cube, I just want to know what fraction this piece is. Now, there's a bunch of different ways you could solve this. There's ratios, there's a few things you could do. But in this case, we need to figure out the force of gravity on it. And I need to tell you this. For any floating object, the buoyant force is equal to the force of gravity. And since we're not given distances, you could either use x, or I'm going to just make it 1 meter by 1 meter by 1 meter. If we do that, first of all, for all floating objects, that must be true. What's the force of gravity going to be on it? Well, we know the density of the ice, we know its volume, and we know gravity. And if you work it out, the force of gravity on it is going to be 9,170 newtons, which means we immediately know what the buoyant force is. The buoyant force also then, because it's floating, must be that exact same value. Buoyant force also has to be 9,170. If it was anything less, the ice cube would be sinking. If it was anything more, the ice cube would be accelerating upward. In this case, since it's floating and we assume at equilibrium, these two forces have to be exactly the same. Excuse me, my 9 up here is not very pretty. So solving this one, we know the buoyant force has to be 9,170. In this case, we're using the volume of, or the density of water, because that's buoyant force depends on the weight of the liquid displaced. And we can figure out the volume of water that this thing's occupying, or must occupy, must be that. Notice that's less than its entire volume, which is 1 cubic meter. So how do we figure this one out? Well, the volume is just equal to the cross-sectional area times the height, or the depth in this case, that this thing sunk to. In this case, we know the volume is that. Cross-sectional area is 1 square meter, 1 meter by 1 meter. And so you can figure out the depth. It's going to sink to 0.917 meters so that it can displace this much water. What fraction does that leave above water? Well, the difference is going to be the remaining distance above water, which is 0.083 meters over 1, which gives us that, or about 8.3%. We're usually told that icebergs float about 10% of themselves above water. In reality, it's usually about 8.3, but it also depends on the density of the ice. Here's an actual AP type of question. A large rectangular raft is floating in a lake. The surface area of the top of the raft is that, and its volume is that, and the density of the lake water is that. Calculate the height of the portion of the raft that's above the surrounding water. In some ways, this is like the ice cube problem, but this time we're given a few more numbers. Now, first of all, figuring out the force of gravity on it. We're not given its mass, but we are given its density, and we're given its volume. Based on those two things, we can actually calculate the mass. Remember, mass is simply density times volume. So in this case, plugging in the density and the volume, gravity's 10, means the force of gravity on it is that, which means we can immediately calculate the buoyant force. What does the buoyant force have to be? It's got to match it exactly. It's got to be the exact same number upward for floating objects, which answers part B already for us. But now we can actually calculate a few more things. We know the buoyant force. We know the density of the liquid that's being displaced, in this case, fresh water. We can figure out the volume of this thing that's being, or the volume of the water that's displaced to produce that buoyant force. In this case, it must be displacing 1.17 cubic meters of water. So that's this area down here. If you can think about all of this, or sorry, this volume down here. I don't want to scrabble over everything else. Which means we can figure out how deep it's going. Again, volume is going to be cross-sectional area times the depth. In this case, I'm talking about this part right here. This is D. And we can actually solve this. Volume we know is 1.17 from over here. Cross-sectional area is 8.2. And so the depth that it has to sink to is 1.43 meters. So the question is, what's that height above the water? We just have to figure out, first of all, what the height of this thing is. We have its volume, we have the cross-sectional area. The height of this thing is 0.22. That is from the top to the bottom of this thing. In other words, from here to here, it's that. So we just have to subtract this distance to figure out what the remainder is. And if we do that, we'll discover it's about 7.68 centimeters above the water. Now part C. What happens if we put some people on this? How many people can you put on this raft before it completely submerges? And they tell us that the mass of each person is 75 kilograms. Well, how much more can this thing support? Well, that's going to be equal to the additional buoyant force that we could generate from this white area that's still above the water. The buoyant force due to this white area, we can calculate. It's equal to its volume, which is going to be the area, 8.2, times this, how high it is above out of the water, which is the answer we got over here, times 10. So the additional buoyant force we could possibly gather if we put the last part of it underwater would be 6,300 newtons. If each person has a mass of 75 kilograms, that means their weight is 750 newtons. If you divide that out, that additional buoyancy can hold up 8.4 people. But because we can't deal with fractional people, the correct answer on this one would be 8 people.